Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed different class of mathematical models and how we can just classify or how we can just define different class of mathematical models we have discussed. And in this lecture, we will just go for the discussion of discrete time linear models in population dynamics. So, first we will discuss about what is population dynamics, then we will just go for a Fibonacci rabbit model, then a linear cell division model, and how we can just use these difference equations with constant coefficients in a linear form, that we will just discuss. So, with the current world human population of more than like 77.2 billions, you might be questioned about the rate of increasing and their survival conditions. So, like J. E. Cohen write the book on how many population can the earth support. Is this, he relates the historical and scientific factors of the same, but the question here is that can we study these factors mathematically? Yes, the stream of bioscience which deals with such questions is popularly known as population dynamics. So, when we will just go for a modeling of the growth of a population as a dynamical system, already in the last lecture I have discussed about the dynamical system. So, if we will just go for this growth of population as a dynamical system driven by biological and environmental process, then it is called population dynamics. This stream includes the study of survival capability of populations with limited resources and by fighting with diseases. Sometimes you can just find this population level always depends on like birth rate and death rate. So, if we will just consider the total population size at a level, then we have to take like a birth rate minus death rate and how this time is affecting relating to the other factors, that we have to also consider. Specifically, if we will just consider all these factors at a time, then we will have a complete population dynamics model. So, if you will just go for like a Fibonacci rabbit model, consider the problem of rabbit generation which was originally postulated by Fibonacci. So, that is why it is called a Fibonacci rabbit model. So, if you will just consider a pair of rabbits, one of each sex is placed on an island. A pair of rabbit does not breed until they are 2 months old. When they are 2 months old, each pair will produce another pair in each month. Let us assume that a function f n is the number of pairs of rabbits present after n months. For n equals to, suppose since we are just starting like initial conditions 1, 2, 3 and so on, we can just consider. For the first month, if you will just see f1, it is just given as f of 1 here, that is the number of pair of rabbits after 1 month. So, this will be 1 here. So, f2 means number of pair of rabbits after 2 months, this will also be 1, since after 2 months they can just give birth of like 1 pair. So, f3, that is nothing but f of 3 here, number of a pair of rabbits after 3 months. If you will just see, first 1 pair was there, they have given like a 1 pair. So, the total pair is a 2 here, and after this it will just continued like the next birth babies, they can be like given birth after 2 months again. Hence, Fibonacci developed a mathematical model considering this linear difference equation, which is in the form like f n equals to f n minus 1 plus f n minus 2 for n greater or equal to 3. Since it is a linear difference equation with order 2 here, so we will have like at best 2 initial conditions, so it is required. So, to deal with that equation or such type of equation, especially we will just go for this linear homogeneous difference equation solution form. So, the general form of this linear homogeneous difference equation of degree k with constant coefficients is written as a n equals to C1 a n minus 1 plus C2 a n minus 2 plus C3 a n minus 3 plus Ck a n minus k, where C1, C2, C3 up to Ck are constants here. Since it is a kth order difference equation, the same number of initial conditions it is required. Let us say a0 equals to small a0 here, a1 equals to small a1 here, ak minus 1 equals to small ak minus 1. So, if you just go for this solution of this homogeneous differential equation, first we will just substitute a n equals to m to the power n here. And if you will just substitute this in equation 1, this will just simplified to a polynomial of degree k here. This is also termed as auxiliary equation. The roots of these auxiliary equations are called auxiliary roots, and these roots helps in getting explicit form of the solution. So, if then we will have these roots of this characteristic polynomial are real and distinct, then the solution will be in the form of a n equals to b1 alpha 1 to the power n, b2 alpha to the power n, up to bk alpha k to the power n. Since the solution it is assumed in the form of like m to the power n, since we will have these distinct roots like alpha 1, alpha 2 up to alpha k. So, that is why in place of m we can just put alpha 1, alpha 2 up to alpha k, we will have this is the solution, where alpha i's are the roots of this polynomial and b i's are obtained after substituting those k initial conditions. Since they are like a constant coefficients, so it can be obtained if you just put the initial conditions for I equals to 1, 2 up to k there. If any one of the roots say alpha 1 has multiplicity m, sometimes if a double root is existing, both the roots are same, then in that case the complete solution or this auxiliary solution of this equation will be in the form of a n equals to b1 alpha 1 to the power n. So, simply we can just multiply n here, n b2 alpha 1 to the power n of 2, since the number of roots, if you will just consider here multiplicity m here, then we will have n to the power m minus 1 bm alpha 1 to the power n plus bm plus 1 alpha 2 to the power n. It is the next root, immediate root. Since we will have like alpha 1 has the multiplicity m, then other roots are also existing there. So, that is why other roots it will be written in the form that we have just explained in the earlier solution. If the roots are in complex conjugate pairs, say alpha equals to u plus or minus iv, then this will lead to the solution in the form of b1 r to the power n sin n theta plus b2 r to the power n cos n theta, where r square can be written as u square plus b square and tan theta can be written as v by u for theta lies between 0 and pi here. So, theta is a lesser equal to greater or equal to 0 and it should be less than pi there. So, if we will have this system, then we will just go for this stability condition of this linear homogeneous differential equation. In the first lecture I have just told that if you will have a system, then the system should be stable and the system should be consistent. So, once we are just getting these solutions, whether this solution representing a stable solution or not, that we will just go to test. If alpha I is less than 1 for all I equals to 1, 2 up to k, then all the roots lie inside the unit circle and hence tends to 0 as n approaches towards infinity. This leads to a stable condition asymptotically. If you will just see here, suppose if you will have a circle here, then this condition is just coming like this form here towards the origin. So, that is why we are just saying it is asymptotically stable. And if alpha I less or equal to 1, at best one of the alpha is 1 there for all I equals to 1, 2 up to k, then it is called stable condition. This means that you will have a like a constant value there and we will have like a straight line in that sense. If any one of the roots say alpha I greater than 1, then it diverges and hence make the system unstable here. And if we will just go for the analysis of this Fibonacci rabbit model here, then this mathematical representation of this Fibonacci rabbit model is fn equals to fn minus 1 plus fn minus 2 for all n greater or equal to 3. And to solve this, suppose if you will just put here fn equals to m to the power n, hence we will have this characteristic equation that is in the form of m square minus m minus 1 here, this equals to 0. Since directly if you will just put here fn equals to m to the power n, in this equation here, then we will have this equation there. And the root for this quadratic equation will be in the form of m equals to 1 plus or minus root 5 by 2, and the required solution whatever we have just explained in the previous slide, that can be represented as f n equals to c 1, since constant it will be there, 1 plus root 5 by 2 whole power n, plus c 2 1 minus root 5 by 2 whole power n here. And if you will just use the initial conditions, the solution will be like f n equals to 1 by root 5, 1 plus root 5 by 2 whole to the power n, minus 1 by root 5, 1 minus root 5 by 2 whole to the power n here. And if you will just see here that for all n belongs to n, we will have a natural number here, since in this equation if you will just see all the irrational numbers are involved, and in analysis always we can just find that when the irrational numbers are involving any expression, then always they are producing a irrational number. But the beauty of the equation is that you can have a natural number when you can just assume any natural number which is in the form of n here. So again, since one of these auxiliary roots is greater than 1, so this equation will approach to infinity as n grows with order of like epsilon to the power 1.618, which is nothing but 1 plus root 5 by 2 value here, that is especially called golden ratio, where epsilon is defined as f n plus 1 by f n here. Then we will just go for a linear cell division model. Assume that a cell division takes place concurrently, and at each time cell is producing suppose alpha number of daughter cells. So in that sense, first we will have like big cell, then this division takes place. So then we will have like a different cell size or a different distribution of cells, and the number or density of cells at the beginning of cell division process is suppose C0 here. After n generations, number of cells can be Cn, suppose given as a Cn equals to alpha Cn minus 1, where n belongs to n, n equals to generation number here. This model is in the form of simple linear difference equation and also known as Malthus model here. And this model is named after famous English economist Thomas Robert Malthus developed this model. So now in this model, if you will assume that cells are producing themselves at a rate of b, and simultaneously cells are extincting at a rate of d, suppose the cell population is changing only due to births and deaths of cells, that is without any migration effect, then we can just write Cn minus 1 gives the difference of numbers of births and deaths over the interval Tn minus 1 to Tn there. If v and d are constants, then Cn minus 1, it can be represented as b minus d Cn minus 1 here, or Cn can be written as 1 plus b minus d whole into Cn minus 1, which can be written as alpha to the power n C0, where n belongs to n, if alpha equals to 1 plus b minus d here. If further migration of cells is allowed with a constant rate of migration, suppose m here, m greater than 0. So especially we are just considering m greater than 0 for immigration and m less than 0 for emigration here. Then evolved model will be like Cn equals to alpha Cn minus 1 plus m, where n belongs to a natural number. This equation is in the form of a linear non-homogeneous difference equation, and stability of this m can be analyzed from the previous analysis. So if you will just go for this linear non-homogeneous difference equations, then the general form of this linear non-homogeneous difference equation of degree k can be written as a n plus d1 a n minus 1, d2 a n minus 2, d3 a n minus 3, dk a n minus k, this equals to f n, suppose. If f n is identically 0, then above equation turns into a linear homogeneous equation. If f n is not identically 0, then the solution of a n can be defined as complementary function plus particular function here. So where the CF represents here complementary function and PF is the particular function here. And this complementary function can be calculated from the method described for linear homogeneous equation but for the particular function it can the value of this function depends on the forcing function f n there, since f n represents the right hand side of this equation here. For calculating particular function, there is a big role of auxiliary equation. So, auxiliary equation already you have known that one. Let Gm is the corresponding auxiliary equation of a homogeneous part of a non-homogeneous equation after substituting n equals to m to the power n. Especially whenever we are just discussing this linear non-homogeneous difference equations that differs from this like continuous difference equations. That is, continuous difference equations means we can just say that it is a differential equations. And in case of this difference equations, if you will just see here that we will have two types of solutions, that is, one is called your complementary function, another one it is called a particular function here. And for the complementary function especially we are just putting that variable, it is in the form of like m to the power n. Then we are just determining these roots. If you will just see the slides here, that if you will have like a polynomial that is of order n here, that is a n plus d 1 a to the power a n minus 1 d 2 a n minus 2 d 3 a n minus 3 up to d k a n minus k, this equals to f n. Then when we will just go for the solution of this difference equation, we will have two parts here. One it is called complementary function part, another one it is called particular function part here. So, if you will just find this complementary function, then we have to put a n equals to m to the power n here. And if you will just put a n equals to m to the power n, then we can just reduce this polynomial that is in the form of like m to the power n plus d 1, then we will have m to the power n minus 1, d 2, m to the power n minus 2 plus up to d k m to the power n minus k, this equals to 0 here. And if you will just take common here, that is as m to the power n minus k, which is a lowest order term of m here, then we can just write this one as a m to the power k plus d 1 m to the power k minus 1 up to d k, this equals to 0 here. And if you will just see here, then m to the power n minus k, which is not equals to 0, then we can just consider this polynomial of degree k, that is especially we are just writing it as here as a g of m, this equals to 0 here. And if you will just find the root of this equation g of m, which will provide the characteristic roots for this difference equation. And if we will just evaluate this characteristic roots, then we can just write this characteristic roots as in the form of like a complementary function, which takes the values are in the form of like if you will just write here, then our solution it is written in the form of a n equals to m to the power n. So, that is why whatever this order of this equation, it will just involve the same number of arbitrary constants, it will involve for this complementary function also. So, that is why the solutions can be written in the form of like complementary function, which can be written as, if you will just see here, that is a alpha 1 your variable that is in the form of m 1 here. So, m 1 to the power n, alpha 2 m 2 to the power n. So, likewise we can just write, since it generates a polynomial of a degree k here. So, alpha k m k to the power n is the complementary function. And if you will just go for this particular function here, then this particular function can taken as like, since our earlier value, if you will just see here this difference equation, that it has been reduced in the form of g of m, and if you will just write this particular function for this complete difference equation, that is in the form of this one here, then this variable a n can be written as 1 by g of m operated on this right hand part, that as f n here. And if you will just operate this one, this is nothing but the particular function of a n here. So, especially whenever we are just operating this 1 by g m function with the f n, we will have like different conditions here. For the first case, if you will just choose here f n is equal to a to the power n, then like our continuous case, whenever we are just using this ordinary differential equations, then especially we are just assuming this generalized solution that is in the form of y equals to e to the power ax, then we are just writing this particular function. If the function is in the form of like yp, then especially if 1 by f of d, if it is operated on e to the power ax, we have just replaced this one by the form of e to the power ax by f of a. Similarly, in case of discrete values, that is in case of difference equation, if you will just apply here f n as a to the power n suppose, then we can just write this particular function as 1 by g of a to the power n. But the question arises that if g of a equals to 0 here, if g of a is not equals to 0, then directly we can just write 1 by g of a to the power n, since it is a geometric series here. But if g of a equals to 0, then this particular function can be written as 1 by m minus a whole to the power k a to the power n here. Especially if you just go for this like our continuous case, that is in a different ordinary differential equation case, there also if we are just writing this f of a equals to 0 there, then we have just replaced yp as in the form of 1 by f of d plus a, and which is operated on e to the power ax. So, e to the power ax operated on 1 here, that is b of x function. Similarly, if we will just go for this geometric expression here, then we can just write this particular function as 1 by m minus a whole to the power k, since it generates a polynomial of degree k, that is g of m, and which operated on this function a to the power n. And if you will just see here, this represents a like a combination series, that is in the form of nck a to the power n minus 1. Since this is a geometric series up to n minus 1 terms, we can just consider that is in the form of k here. That is why it has been written in the form of first term. If you will just see, it can just take as the constant term, then simultaneously it will just increase. Likewise, if you will just see like sin x, suppose sin x means it has a Taylor series expansion, first term it just takes a constant value there 1. Then especially it can just incremented afterwards. So, if you will just take the geometric expansion of this function, which involves this power function here, and which has this denominator parts takes the 0 value, then we can just write this particular function as nck a to the power n minus 1. And similarly, the next case is that whenever we will have this function that is in the form of like f n equals to n to the power p here, and if you will just put this f n equals to n to the power p here, then this particular function can be written as 1 by g of m. So, whatever it is just written there, then it is operated on f n function, that is as n to the power p here. So, p is any like arbitrary constant here. And if we will just write in this form here, then we have to use certain difference operators to get this particular function here. The difference operator that is used for this class of problem is that forward difference operator here. So, forward difference operator, if it is operated on this function, that is a bracketed function we have just defined, this bracketed function is defined in the form of like bracketed of n, it can just take the value as n here. And if we are just taking this bracketed function, that is n square here, which can just take the value as n into n minus 1. If you will just take this bracketed function of n cube, then it can be written as n into n minus 1 into n minus 2. Especially if you will just see this bracketed function here, then whatever this power or order it is just written here, that takes the number of terms before that, and it is just taken as a product form there. So, that is why it is just represented as a factorial notation. Especially if you will just take this power of this bracketed n as r here, then especially it will involve r terms. So, that is why we have just written as the product of n into n minus 1 to n minus r plus 1 terms here. And we have known that whenever this difference operator is operated, that is like forward difference operator. So, if we are just assuming a function f of x, which is written in the form of f of x plus h minus f of x, this is the forward difference operator formula. And if we will just assume suppose f of x is a polynomial, suppose like x square, then if we will just use this difference operator here, that is with space size suppose h here, then we can just write del of x square, which can be written as x plus h whole square minus x square, which can be written as x square plus 2x h plus h square minus x square here. And if you will just see here, so x square it will just cancel it out, and we can just write here that is in the form of 2xh plus h square here. And next time if you will just apply this del operator here, so if del will operated on a constant function, that will just provide you like another, if you will just apply del square of x square here, then this will just provide you del of 2xh plus del of h square. So, h square, since h is a constant here, so h square minus h square, this will just give you 0 value, and especially if you will just use for this function here, then we can just write here as 2 of x. So, that is why x plus h minus h, since only here if I will just see here only x it is there. So, if I will just use this function f of x equals to x only, so first value it can be written as f of x plus h. So, that is why x plus h minus this is f of x as x here. So, x cancel it out, so it will just provide you 2h square. So, if you will just keep this space size h equals to 1 suppose, then we can just write del square of x square, this equals to 2. Similarly, like derivative here. So, if same way we can just use this del operator for this function here n to the power p, we can just write this one as p n to the power p minus 1, since we have just seen that if del operator, if it is used for x square here, so then if you will just consider the space size h equals to 1 here, especially this can be written in the form of like 2x plus 1 here, and the first term if you will just see, that is nothing but 2x it is there. So, that is why this difference operator if you will just operated here, that can be written as a p n to the power p minus 1 here. And if you will just consider suppose this f n as a like a trigonometry function here, trigonometry function means if these roots are coming in the imaginary form, then we can just write this functions are in the form of cos of x plus I sin of x. So, that is why this function if we can just write as cos x or sin of x here, that is in terms of n, if you will just write cos of k n and sin of k n, then this particular function can be written as 1 by 2i into 1 by g m e to the power I k n plus or minus 1 by g m e to the power minus I k n, where m equals to, especially it can be written as exponential of I k, since exponential of I k means we can just write this as cos of k plus I sin of k. And if g of m equals to 0, then we can just follow this previous procedure to get the solution here. Based on different cases of linear homogeneous differential equations, we have considered one example where we have considered this equation as y n plus 2 minus 4 y n, this equals to 2 to the power n plus n square minus 1, with the boundary conditions as y of 0 equals to y 1 equals to 0 here. Especially if we are just going for this solution of this linear homogeneous differential equations, we have to consider one complementary function and one particular function, and the total solution it will be like sum of this complementary function and particular function. In case of ordinary differential equations, that is in a continuous case, here we are just considering this discrete cases. So, in continuous case we have just assumed this function as y equals to e to the power m x to find these complementary functions, and here we are just using one geometric expansion, that is in the form of like y n equals to m to the power n to get this complementary function here. So, if you will just put suppose y n equals to m to the power n in this equation, so we have this equation is in the form of y n plus 2, that is minus 4 y n, this equals to 2 to the power n plus n square minus 1 here, and directly if you will just put here, that is y n equals to m to the power n as a geometric expansion here, then for the complementary function we have to keep it as like complementary function of yn, this can be written as like m to the power n plus 2 minus 4 m to the power n, this equals to 0 here. This implies that m to the power n into m to the power 2 minus 4, this equals to 0, where if you will just see m to the power n, this is not equals to 0. So, that is why we can have like m equals to plus or minus 2 here. And if we will just consider m equals to plus or minus 2, then we will have two real and distinct roots here. And if you will just see here the polynomial that is expressed in the form of gm, that takes as m square minus 4 here. Since g of m is a polynomial for degree 2, the solution for this complementary function that will involve two arbitrary constants. Hence, the solution for this complementary function yn can be written as like c1 m to the power n. So, that is why we can just write 2 to the power n plus c2 minus 2 to the power n is the complementary function here. So, if you will just see here that we will have this auxiliary roots, that is m equals to plus or minus 2 here. So, the complementary function for yn, it is expressed in the form of c1 2 to the power n plus c2 into minus 2 to the power n here. Then we will just go for this particular function. So, if we will just go for this particular function here, then we have to consider like the particular function of yn, which can be expressed in the form of like 1 by g of m 2 to the power n plus n square minus 1, and this can be written in the form of like 2 to the power n by g of m plus n square by g of m minus 1 by g of m here. And already we have discussed that if any function that is in the form of a to the power n by g of m is existing, then directly if g of a is not equals to 0 there, then we can just write that function as a to the power n by g of a. If you will just see this previous slide here, that you can just find that particular function of a to the power n, which can be expressed as 1 by g a to the power n if g of a is not equals to 0 here. So, that is why if you will just see here the particular function for 2 to the power n here, then we can just find that. So, 2 to the power n directly if I will just write here particular function of 2 to the power n by g of m, this can be written as 2 to the power n by g of m. So, g of m is nothing but m square minus 4 here. So, which can be written as 2 to the power n by m plus 2 into m minus 2 here. So, first we will just do this partial fraction to get the independent form of this m plus 2 and m minus 2 in the like denominator side here. So, that is why if you will just use the partial fraction to get this division form of this m plus 2 and m minus 2, we can just write this one as 1 by m plus 2 into m minus 2, this equals to a by m plus 2 plus b by m minus 2 here. And if you will just try to find the solution here, then we can just write here, that is a into m minus 2 plus b into m plus 2, this can be written as 1 here. If we will just take this coefficients of m, which can be written as a plus b equals to 0, then we will have like minus 2a plus 2b, this equals to 1 here. From the first equation if you will just see, this implies that a equals to minus b here. So, if I will just replace here directly minus 2a minus 2a, this equals to 1, this implies that a equals to minus 1 by 4 here. And since we have written here a equals to minus b, so that is why b can be written as 1 by 4 here. And finally, we can just write this coefficient as in the form of like 1 by minus 1 by 4, since a by m plus 2 to the power n plus 1 by 4, this one is your m minus 2 to the power n here. And already we have seen that in case of like 1 by m minus a, sorry, this is g of a is not equals to 0, we can just write that one as 1 by g a to the power n. So, that if you will just see from this slide here that 2 to the power n by m plus 2 here. So, directly if you will just replace here m by 2, then directly we can just write this one as minus 1 by 4 2 to the power n by 4 here. This is the first part of the solution. And second part, if you will just see here that this g m part, this just take the 0 value whenever we are just putting directly m equals to 2 here. So, for this we will just use the other formula, that is in the form of like if you will just see here, that is 1 by m minus a whole to the power k a to the power n, this can be written as n c k a to the power n minus 1. So, that is why if you will just see here that k is 1, that is the first root, since we are just writing there m minus 2 only. So, k is 1. So, we can just write that one as n c 1 a to the power n minus 1 is the particular function for that part. So, that is why we can just write this one as plus we will have n c 1 and then second is a 2 to the power n minus 1 into 1 by 4, whatever it is just present there. So, finally, if you will just see this particular function for 2 to the power n by g of m, so that can be written as like here, that is 0.25 into n 2 to the power n minus 1 minus 2 to the power n by 4 here. So, that we have just derived there. Next part is that if you will just see here, first part it is over. So, next part particular function of we will have n square by g of m. So, if you will just see here, this is written in the form of n square by g of m is n square minus 4, and which is nothing but if you will just see our previous slide here, then this is just taking in the form if f of n equals to n to the power p, then the particular function of 1 by g of m n to the power p, which can be written as 1 by g of 1 plus delta into n to the power p. So, directly we can just write there as 1 by g of 1 plus delta n to the power p. So, if you will just see here, we will have g is written as in the form of m square minus 4. So, that is why g of 1 plus delta, it can be written as 1 plus delta whole square minus 4. So, which can be written in the form of like 1 plus delta square plus 2 delta minus 4 here, and which can be written as minus 3 plus delta square plus 2 delta here. And directly if you will just write here the particular function of this one, which can be written as, so you will have like denominator side, that is 1 by minus 3 plus delta square plus 2 delta operated on n square here. So, since we cannot operate this operator in a like if you will just keep this one in a denominator part, we cannot operate that one. So, that is why we have just kept it into the numerator part here. So, that is why to get it in numerator part, we can just write this one as like if you will just take common here minus 1 by 3. So, 1 by minus 1 by 3 if you will just take common. So, then we can just write this one 1 minus del square plus 2 delta by 3 here operated on n square, and which can be written as, so minus 1 by 3. So, this is a 1 minus delta square plus 2 delta by 3 whole inverse operated on n square here. So, already we have known also that if we are just using these operators, delta operators on this factorial form, then it is easy to handle. So, that is why our first aim is that we have to convert this n square into the factorial part here. So, if you will just see here, first we have just tried to convert this n square into the factorial part. So, that is why we are just writing this n square as in the form of n into n minus 1 plus n here. So, if you will just see this part here, then it can be written as n square minus n plus n, which can be written as nothing but n square here. And if we want to write this n square in factorial form, then this factorial n square, which can be written as n into n minus 1, and factorial of n, it can be written as n only. So, that is why we can just write or shift this n square value as in the form of n into n minus 1 plus n here. So, that is why we can just write this one as bracketed n square plus bracketed n here. And if you will just see here, we have already taken common, if you will just see here, that is a minus 1 by 3, 1 minus delta square plus 2 delta by 3 whole inverse. So, it is just converted to now this is factorial n square plus factorial n here. And now, if you will just take this expansion here, so then you can just find that this expansion can be written as minus 1 by 3. So, take this binomial expansion 1 plus delta square plus 2 delta by 3 plus delta square plus 2 delta by 3 square plus delta square plus 2 delta whole cube. So, likewise we can just do this expansion operated on bracketed n square plus bracketed n here. And already we have known that this delta operator, that is nothing but our forward difference operator only. So, delta of f of x, which can be written as f of x plus h minus f of x. So, if delta is operated on a polynomial form here, so suppose if I will just operate delta on x only, so which can be written as x plus h minus x, so which can be written as only x here, h here. So, if h equals to 1 here, then we can just write delta of x is nothing but 1 here. And similarly, if since we are just operating this delta function on this factorial forms here, so if suppose we are just operating delta square on suppose this bracketed x square here. So, bracketed x square means it can be written as delta square x into x minus 1 here, which can be written as delta square x square minus x here, and which can especially written as x plus h whole square minus x square minus x plus h minus x here. And if you will just expand this x plus h square here, which can be written as x square plus h square plus 2xh minus x square. So, x square it will be cancel it out, minus this will be like x minus x, it will just cancel it out. So, minus h it will be there. So, we will have like first delta we are just operating. So, that is why we can just write a delta of this one delta of this one only. So, that is why first delta it has been operated. If you just operate the second delta, then we can just find that h square means it is a constant. So, it will take the 0 value. So, if it will operate on h, it will also take the 0 value. So, next if you will just operate on this value here, so it will just take 2h into x plus h minus x here. So, it will just provide you 2h square, and if you just put here h equals to 1. So, delta square of x square, this is nothing but 2 here for these difference operators. So, similarly, if you will just see here delta square, if it is operated on n square, this will just giving you a constant here, and similarly if 2 delta it will be operated on n here, so it will just give you a constant value. But if delta square it will operated on n here, so that will just give you a 0 value here. So, if you will just eliminate all these operators, so then you can just find this operated value as bracketed n square plus 7 n by 3 plus 20 by 9 here. And finally, if you will just multiply this minus 1 by 3 into bracketed n square this one. So, bracketed n square means we can just write this one is n into n minus 1 plus 7 bracketed n means this is 7 n by 3 plus 20 by 9. So, it will just take the value as minus 1 by 3 into n square plus 4 n by 3 plus 20 by 9. And this one usually you can just visualize from here also, that is first value if you will just write here, that is minus 1 by 3 bracketed n square plus bracketed n. Second value if you will just operate this one delta square n square here. I have explained also this one in the previous slide, if you will just see here, that is delta of n to the power p, it can be written as p n to the power p minus 1 here. So, same way we can just express also there, that is a delta of p n, which can be written as n p n minus 1, sorry n p, this is p n p minus 1. So, if you will just see here delta of n to the power p, directly we can also visualize here that delta square if it is operated on n square here. So, directly if you will just put this one, so it will just give you 2 n, first operator it will just give you 2 n, then the second operator if you will just do, then it will just give you 2 only 2 here. Similarly, if you will just operate delta 2 delta on n square or bracketed n square, so it will just give you 2 n here. Similarly, if you will just operate delta square on bracketed n, this will just give you 0, and 2 by 3 delta if you will operate on n, this will just give you 2 by 3 here. So, that is why if you will just write here, so first value it will just give you 2 by 3. So, then 2 delta if it will just operate, so it will just give you 2 by 3 into 2 n, and immediate next value if you will just use, so it will just give you 2 by 3. Then the next immediate next value if you will just apply here, so we will have like del to the power 4 plus we will have like operated if you will just see here del to the power 4 plus we will have 4 del square, then we will have like 4 del q by 3 operated on bracketed n square plus bracketed n. Since after this you can just find all other values are 0, since higher order differences it will just give you 0 value there. So, from this only you can just find this particular values, that n square plus 7 n by 3 plus 20 by 9 here. So, hence if you will just see here 3 particular functions we have just obtained, then these 3 particular functions it can be added together to get this complete particular function for y n here, and the general solution it will be like y n equals to first the complementary function plus particular function. So, that is why this complementary function it can be written as like c 1 to the power n plus c 2 minus 2 to the power n, this part it is just written. And second part is that is particular function which can be written as like 0.25 n 2 to the power n minus 1 2 to the minus 2 to the power n by 4. Second particular function if you will just see, that is nothing but minus 1 by 3 n square plus 4 n by 3 plus 20 by 9. Last one if you will just see here, that is remained is minus 1 by g of m here, minus 1 by m square minus 4 here, and which can be written as like only 1 by 3, since directly if you just put this value, that is minus 1 by minus 1 whole square minus 4 here. So, it can be written as minus 1. So, it will be just taken as if you will just see here minus 3 here. So, particularly it will just take 1 by 3 value. So, 1 by 3, and if you just find this complete solution based on this initial conditions, the particular solution will be in the form of, since we have to put this boundary conditions also, that is in the form of y 0 equals to y 1 equals to 0, then the total solution it will be in the form of 7 1 by 3 by 1296 2 to the power n minus 26 by 324 minus 2 to the power n plus 0.25 n 2 to the power n minus 1 minus 2 to the power n by 4 minus 1 by 3 n square plus 4 n by 3 plus 20 by 9 plus 1 by 3. It is easily obtained, since directly if you just put these values like y n is given here. So, if you just put here that y 0 equals to 0 here. So, 0 equals to, you can just put C 1. So, first value this is a 2 to the power 0 plus C 2 0 also. So, all remaining values if you will just see here, that will just 0.25. So, n is 0. So, minus 2 to the power n by 4 here. So, it can just take the value, then minus 1 by 3, n equals to 0, n equals to 0, then 20 by 9 plus 1 by 3. So, from this equation we can just separate C 1 and C 2. We will have two equations, since the next equation we can just put this one as y of 1 equals to 0. So, this means that n equals to 1 we will just put, and y n total value is 0 here, and we will have like two set of equations, and from there itself we can just find C 1 and C 2 value. So, once you are just obtaining the C 1 and C 2 value, directly you can just put the C 1 value as this one and C 2 value is this one here. So, this is the final solution for this problem here. So, if you just go for the analysis of a linear cell division model, the mathematical model representation of a linear cell division model is given as equation 2.9. If you will just see the previous slide here, that is C n equals to alpha C n minus 1 plus m here. So, C n minus alpha C n minus 1, this is a m for n belongs to n here. If m is treated as a constant here, the solution of above equation after substituting initial condition can be written as C n equals to C 0 alpha to the power n plus m by m minus alpha into 1 minus alpha to the power n here. And next step is the stability analysis. For stability analysis, alpha has the possibilities like alpha equals to 1. So, if we will just consider alpha equals to 1, this implies that a constant population of cells, then we will have a stable condition. If we will just consider alpha greater than 1, then we will have like a no cell, number of cells goes to infinity as generation progress, then we will have a unstable condition. If alpha less than 1, then we will have like the population will extinct at generation progress, we will have a asymptotically stable condition. So, now we will just conclude this section. So, first we have discussed the introduction of this population dynamics, then we have just discussed about this Fibonacci rabbit model and how this formulation has been framed and how we are just obtaining the solutions. Then we have discussed about different class of linear differential equations with constant coefficients, and we have also discussed a nonlinear class of models. Then we have discussed like different linear cell models and their formulations. Thank you for listening this lecture.